Thank you all for coming. Glad to see so many of you out here. We've got this is our third installment of the Fastly Speaker Series, and we're so glad to be able to do this because it's fun for us and we get a chance to hang out with some of the other folks in the San Francisco community and some of the folks online too. As ever, this is intended to bring a couple of the talks from the security conferences that, after a few days of hearing presentation after presentation after presentation, there's one or two talks that kind of stick in your mind long enough to have a real conversation about them or to like inspire you to go look something up, talk about them later when you get back to the office and say, oh, what did you see? Oh, I saw this talk. It was really exciting. That's what we're hoping to condense the Fastly Speaker Series into, just those talks that we are most excited about after coming back from a conference. So tonight we've got two fantastic speakers, and up first is Alex Bazhaniuk. Okay, well, he taught me how to pronounce it a moment ago, and I'm doing a terrible job with it. He actually asked me to just call him Alex, so we're going to go with that. So Alex is an independent security researcher, and he's going to be speaking about exploring your system deeper, which I'm very excited to hear about. So please welcome Alex.
I am from Eclipsium company. My bio was not updated. We just started the company a couple of months ago. Before that, I used to work about 5 years in Intel in different groups, including the hardware validation, including advanced threat research, which we spent a bunch of time there focusing on different aspects of the firmware security and platform security and virtualization security. And then in 2014, we released some open source framework called CHIPSEC. And but that time when we released that, there was pretty limited use cases. And then we figure out that can be a bunch of more things can be added to the CHIPSEC to help make an investigation in the system, to help find vulnerabilities in the system, create hypervisors, make an investigation for the virtualization environment, like run something from the guest and see what interfaces is emulated in the guest and so on. And this talk, and previously, when we released this framework, we make one presentation about this tool in 2014. And then there was 3 years, we still continue and contribute this, and we never presented what kind of feature it has and what kind of problem we try to solve by releasing this new capabilities in this tool. So that was the motivation of this presentation. I've presented this presentation in some conferences, started in the CanSecWest this year, and you may ask why I'm still presenting this. There was like half a year and I presented the same material. And the answer will be in one of the slides, but the short answer like that. I've purchased recently the couple laptops for some of my tests. High-end laptops, Kaby Lake laptops, and then I figure out that there is simple test which already exists in CHIPSEC around 5 years, still failing. So there's still common vulnerabilities in a laptop after we released this test 5 years ago, and still vulnerable system we have right now. So that was sort of why I'm still presenting this talk, and I still think there is a bunch of stuff which is supposed to be fixed, and a bunch of new capabilities which CHIPSEC has, which we need to know and use it for the future investigation, either for incident response or for just find vulnerabilities in the BIOS. So I will go through introduction to the firmware security, then how to find vulnerabilities in the firmware using the CHIPSEC. Just recent one, not all of the vulnerabilities, just whatever we saw in 2016, 2017. Checking hardware protections, the one which exactly supposed to be fixed, but it still has a bunch of system which is not fixed, that the hardware protection problems. How to find implants, some of the interesting concept about how we can find implants, including small demo, and how we can use the same framework to analyze the virtualization environment and hypervisors. So what is firmware is? So firmware is some code which is running on some of the controller or in the main CPU, if you're talking about system firmware. And if we'll see the diagram of the modern system, we'll see there is a CPU, there is a memory controller and memory, there is PCH, and the PCH connected to the SPI controller, there can be TPM, there can be network cards, there can be USB devices and so on, and a bunch of them has the firmware. Some of them is documented, some of them is not documented, some of them is, has the API, some of them is not. And the interesting part is that if there are any vulnerability in some of them, and if they are not good documented and you don't know how to check that vulnerability or you don't know how to extract the firmware, you might have a trouble to even check that your system is vulnerable or not. In many cases, you can check, at least based on the versioning, but there is still many of them don't have the capabilities even to read the firmware. And then if even they have the capabilities to read the firmware, like some of the, say, hard drives, not all of them has some of them has the capabilities to update the firmware, but not all of them has the capabilities to read the firmware. So you can update something, but you cannot read it. But even if you read it in some different hardware firmware, it doesn't mean you understand the layout of whatever you're reading, and you understand where is the part which you can sort of compare with the other knowledge, with other hashes or hashes from vendor. So you need to also after you read the firmware, you need to understand the layout. So then after that, you might to measure something. So there's a bunch of different firmwares. This presentation will be mostly about main system firmware, about BIOS and UEFI. Later on in the end of this year or in the beginning of next year, we will have some presentation about different firmwares as well. So why firmware attacks is really important? So first of all, because if from the kernel you can compromise the firmware, you can make the really persistent implant, meaning some of the malicious code can be injected in some of the software which will survive after reboot, after installation operation system, and even if you replace the hard drive, it can still survive because it will infect the firmware, and the firmware itself living in a SPI controller, in SPI chip, which is basically a special controller which is necessary to run the boot flow in a system. And all of the x86 system, pretty much all of the x86 system, has the SPI controller with the SPI memory and the BIOS there. So if there is easy way from the kernel to make a privilege escalation to the BIOS, it may be fully persistent, fully stealth, so it will be really hard to detect because it may spoof all of the hardware interface when you try to read this from. It may survive again reinstallation operation system and so on. It can be used to bypass also different OS protection methods, and also can be part of the advanced attacks when the attackers has a physical access to the system. Somehow, even if there is not vulnerability, but the attacker may just find the SPI controller in a motherboard and connect to the SPI programmer and override the SPI chip. So in this case, it can be a part of the sophisticated attack when instead of going through the remote code execution, then through local privilege escalation, then compromise the system, the attacker will have the physical access or somehow compromise the firmware, and attack is going from opposite direction when the firmware is infecting the operation system, and then by dropping the file in operation system, it also dropping the file which may have a communication to the malicious backend. So firmware is part of the security scope because it can be, again, really persistent, really stealth, and part of the sophisticated attack. So previously we saw some incidents which is related in the wild, which is related to the hardware and firmware security when there is attacker using some different things, different vulnerabilities or different attack scenario try to compromise the firmware. So some of them was pretty old, from 2008, 2009, like MIBROMI, when they tried to use the BIOS update methods to compromise the BIOS itself. Then there was Equation Group. There was a hard drive implants. Back in the days, there was not many hard drives signed the firmware, so you can, by knowing the protocol, knowing API, and knowing the format of the update, you can update the firmware in the hard drive, and then use that to hide some of the data in hard disk or to exfiltrate some other data from the hard disk. The samples was discovered a couple years ago, but I still didn't see the good analysis of the hard drive reprogrammer in the public. Then there was a hacking team. One of the first UEFI-based rootkits or implants. So where that leak has happened, there was the source code and the binaries of this rootkit. So you can basically download them and investigate. We have a couple slides about that as well. And there was recent, probably this year, in the beginning of this year, there was Vault 7 leak. Some of the data about the UEFI, the Mac UEFI implants. That one was really interesting because of two reasons. This one was UEFI-based implants, which is first implants which is using vulnerabilities in the installation process. So the hacking team make an assumption that the BIOS is open, fully open, doesn't have any protection, or you have a physical access to the system. So the Vault 7, they are not making this assumption. They are actually trying to exploit vulnerabilities to inject the implants to the spy chip. Another interesting part of this one was that it is surviving updating the BIOS. According to the documentation, there is no sample. There is no sample, there's just some documentation. And according to the documentation, during the infection phase, after infection has happened, if there is any BIOS update came, the infector is reinfecting the BIOS, the update package to making sure that after the BIOS is updated, there will still be infected system. Pretty interesting, at least in concept perspective. So as I mentioned, this talk will be mostly related to the open source framework and how we can use it for many different things. So it is on GitHub, you can download it. It has also pip package, although no one updated it about 5 months, so maybe pretty old. We need to update this. It supports x86. This year we have internally added support for the ARM. It's not public, it's not open source yet, but it will be open source, I believe, by the end of the year. We will have ARM version of the CHIPSEC, and we will have a presentation which is using this ARM version of CHIPSEC to compromise hypervisor in some of the Qualcomm SoCs, which we presented in Black Hat this year. If you don't see it, I recommend you to check it out. Let's start going with vulnerabilities. One of the biggest vulnerabilities which was discovered about 3 years ago was S3 boot script vulnerabilities. So the idea of this vulnerability is like that. When your system going to sleep and waking up, when the system is waking up, the system is supposed to be initialized properly. And you don't want to run the BIOS again, because the BIOS is pretty heavy, a lot of code. There is a lot of modules there. There is like millions of code of there. But you want to initialize the system from when you're waking up from the sleep properly, but you don't want to run entire BIOS. To doing this, there was a S3 boot script. There is a special script which we designed it exactly for initializing the system when you waking up the system from the sleep. And it's sort of in temperature, and you have opcodes in that temperature. And opcodes is basically defining how supposed to configuration be set. And this vulnerability was pretty interesting because it was really reliably exploitable, really easy to find. So the idea was like this. The script was in unprotected memory. And then if you can find this in the memory, you can modify, then you put the system on sleep, you're waking up, and then your code is running from there. And an interesting part is that if you modify a serial script early enough, you can override all of the locks and unlock the system. So after the system came from the sleep, the system will be locked because you remove all of the locks from the script. So if the script is accessible, there's definitely can be a problem there. Also, there was a problem because there are some things which is not implemented in interpreter, like MSR registers set, like MSR write, MSR read. That's not implemented in interpreter. But when we set in configuration, we want to set the MSRs. To doing this, there was opcode calling dispatch, which is basically just calling the x86 code. So basically, if you controlling the dispatch opcode or others where this dispatch opcode is calling, you basically can call any random malicious code and you execute it before the configuration is set, or you can or you can disable some protection and so on. So pretty serious vulnerability. We have a test which you can run and check your system for this vulnerability. In 2015-16, there was like about 80% of laptop was vulnerable. Nowadays, it's much better. So if you have a recent laptop, it may not be vulnerable. But the interesting part of this test, that this test is not checking all of the cases. This test is checking just the cases which is accessible from the kernel. But for example, there is another vulnerability, interpreter. So the interpreter which is executing this opcode supposed to be protected as well. And if it's stored not in protected memory, it can be also overridden and used for attackers to make a privilege escalation to SMM or compromise the BIOS. But there is no easy way to check this. So if you're not a BIOS vendor, it's not really easy to just run a test and check it. So this test is not complete. It's just checking some conditions, but it's not checking all of the conditions. And I can imagine if it's not checking all of the conditions, there may be cases then there's still some vulnerabilities there, which we just cannot test. We published the big report, which is explaining all of the different variations of this vulnerability. So you can take a look there more deeply. So that's the example for the Mac UEFI. So before S3 boot script, the configuration was set. After S3 boot script, you check in the PI register, and they are not set. To run a test, this is simple as just running CHIPSEC main without modulus or we specify some module, save the result, then you put the system on sleep, and then you resume it, and then you run CHIPSEC main again. With the modules or without, it's not really important. This one is just checking specific vulnerabilities. When you run CHIPSEC main, it's checking all of the vulnerabilities. In this case, you can check before and after and see how many fails coming from the sleep. If there is no fail, that meaning that your configuration was restored properly. But in many cases, and especially old system, there will be a bunch of things in between. There is a CHIPSEC main module which is checking vulnerabilities, and there is CHIPSEC util, which is basically decoding S3 boot script. So if there is S3 boot script accessible, you can decode it and modify it using the CHIPSEC. Pretty useful. So basically, for example, in some cases, if you can read S3 boot script, it doesn't mean you can write. Some vendor make a fix when they copy the S3 boot script before put the system to the sleep. And in this case, you can read S3 boot script, and you may think the system is vulnerable, but if you try to write it, it will not write. That sort of protection. So not always when you read it, it's vulnerable, but in many cases. In EDK2, the fix was made it differently. In EDK2, it's not even readable. So it's stored in special SMM memory, which will be copied before execute. So it's sort of protecting from read and write. But this sort of fix, it's a good in the perspective of, for the vendor, it's really good. But for us, it's not really good fix because we cannot check the S3 boot script itself. Because it's in protected memory, we cannot read it. And if we cannot read it, we cannot check anything, like what the register it's restoring, is it accessible for write or not? So we just don't know where it is. And it may still be vulnerable, but now we don't know how to check it properly. Next class of vulnerabilities is poison pointer vulnerabilities, which was discovered in 2015. And there's still a bunch of systems which is vulnerable to this vulnerability. This vulnerability is fully rely on implementation. So it's not a platform specific, it's just implementation specific. So the main idea is like this. You have the interface between kernel and SMM, runtime interface, when you can pass the argument to SMI handlers, and SMI handlers inside the SMM, inside the protected memory, run some code there. It's necessary to support some hardware feature, as well as the BIOS configuration, as well as some counters, and so on. And this interface between the kernel and the SMM is supposed to be properly validated in SMM. So SMM should not trust this interface. In EDK1, the interface is through general purpose register was implemented. In EDK2, it was implemented through COM buffer. And the idea of the attack was like this. So because one of the arguments was the address for the output buffer, meaning that the SMI is writing output value to this buffer, then they put the address of this buffer, address of the SMM, and ask SMM to overwrite itself. So basically, you're passing the address of SMM as an argument to the SMI handler. And in ideal world, the SMI handler needs to take the argument. It's not supposed to trust it. It's supposed to check if the address is overlapping with SMM. Then if it is, just drop the execution and return the error. If it is not, then write the output buffer to this address. But in 2015 and beginning of 2016, there was a bunch of BIOSes. Almost all of them didn't check that the address is this address is pointing to the SMM. So you have the right primitive to the SMM memory, and from there you can make a privilege escalation from the kernel to the SMM at runtime. The concept itself really generic and can be applicable for other platform and other different privilege level. And exactly same attack vector we use it to our black hat presentation when we explore how to compromise trust zone in ARM-based system. Then let's assume that the BIOS is fixing properly this vulnerability, and they're checking that the address is not supposed to be an SMM. But is it always fixed for all of the potential scenarios? We figure out it's not. And if you have something like virtualization based in security, like Windows 10 VBS, when the software is initializing the hypervisor and putting the trusted guest and a trusted guest separately inside the architecture. In this case, if the untrusted guest or malicious guest has access to the SMI, can trigger SMI handler, can trigger SMI event, in this case, the attacker can use the same attack scenario, but instead of overwriting the SMM, it may point the address of the hypervisor or trusted VM to the argument of the SMI to overwrite the hypervisor or the guest. So that's sort of the architecture problem, because SMM doesn't know about layout of the hypervisor, guest OSs, everything. SMM just has working as in a mapping one-to-one, meaning that it's like working as a physical addresses. So SMM doesn't know about guests, about hypervisors, and anything. And if you have capabilities to trigger SMI handler, to trigger SMI event, then you can overwrite a hypervisor or another VM. That was our Black Hat presentation this year, how to bypass Windows 10 VSM. Reference, again, you can check here. The main idea is even if you fix it, you need to be really careful with where the pointer is pointing to. And there is a spec which is now defining where is the pointer supposed to be, so that the agreement between BIOS, hypervisor, and operation system to making sure that there is no overlap with sensitive regions. In CHIPSEC, we create a visor to find this vulnerability. You can run it and check your system, although it will take a couple iterations because some of the SMI may reboot the system. Then when you figure out that this is, when you detect the vulnerability, you can explore if this is the vulnerability without check and you have the right primitive to the SMM, or it is already fixed. By checking this, you just need to point the address back to the SMM and see if system is hacked, then the system is vulnerable. Another class of vulnerabilities which we discovered this year, we call it the MMIO BAR overlap issue. And the concept is really generic and can be applicable for other attack scenarios and other registers. So legitimately, how does the MMIO work? You have the device, PCI device. This PCI device has the MMIO range. This MMIO range is basically the memory which is mapping directly to the device. So every time when you read or write to this region, the transaction is going to the device. So the memory controller knows that this transaction is supposed to go to the PCH, and PCH is redirecting the transaction to the network card or to other PCI device. So and everything is working great, but the address of the MMIO range is stored in a MMIO bar in a special register. And this address is stored in PCI config address space for the specific PCI device. And this register, in many cases, is not lockable, or in many cases, is not locked. So meaning that malicious attacker from the kernel can overlap them. Yeah, PDF doesn't have good animation. So the malicious attacker can overlap the MMIO range with the SMM. What will happen in this case? If the transaction is going from the device to that, it will not go through because there is a protection from the DMA attack, call it CHIPSEC, which is protecting that the transaction is not going through the SMRAM. But the SMIs itself, many of them is using the different MMIO bars to talk to the device. So the SMI itself, they are using these bars to talk to the device. And because of that, if you overlap it, and SMI handler will not check that the bar is overlapping with SMM, you have write primitive. In many cases, it's really limited write primitive when you just flip in the bits, because when you have the operation with the MMIO, many of them is as a protocol. You have read and write in the same time window. And in this case, this will not allow you too much flexibility. But there is a special one, spy bar. A spy bar, this is bar reallocatable. And this one is used heavily when you read and write UEFI variables. When you basically want to read BIOS configuration and add assumption to the BIOS configuration. And this bar is used really heavily, and as you can see, there is a bunch of control there. So because you have a control under the name and under the data of the variable, and you have a bunch of control here. So if you overlap the spy bar with the SMM, and then you write the variable, then you will have the right primitive there. So how vendors supposed to fix it? And many of them is fixed this really great. So every time when the SMI handler triggers, if they want to use spy bar, it's restoring the original address of the spy bar before using it, or checking that the spy bar is the address which is expectable address. So it's not really flexible fix, but it's allowing to prevent this type of issues. In CHIPSEC, we create the visors for this, so you can run it and check the vulnerabilities for this issue. Although the visor is not really easy, because when we're talking about MMIO, there is a bunch of transactions going to MMIO, and you don't know, is it something which is SMM code right, or is there something which is device just wrote or someone else wrote, because the MMIO is sort of memory which is working as a protocol, and the state of this protocol can change it over the time. So you need to have the really smart algorithm to fix false positives. Then, but if you make this and you figure out which of the MMIO bars is you can relocate with SMM and which of the SMI handler is using this MMIO bar. Then you can run another visor and try to understand if there is a possible attack scenario or not. Again, I already mentioned this a bit, but I will have one more slide here about this. So some of these attacks is also applicable if you have the solution which is using virtualization, like virtualization-based security in Windows 10, normal world and secure world. For normal world, the idea was really awesome. You have the normal world, which if someone will compromise normal world, they will not extract secrets from the secure world. And for example, credentials for the domain can be stored in a secure VM, and everything is great, except the normal world has accesses to all of the interface, all of the firmware interfaces, meaning that if there is any vulnerability in the firmware, the normal world can compromise the firmware and then extract secrets, or because it has all of the accesses to all of the interfaces, the normal world can use these interfaces as a confused deputy attack. As I already mentioned, that SMI pointer one. Also, the MMIO bars attack can be also used to compromise the secure world. Instead of overlapping the bar with the SMM, you can overlap the bar with the secure world and make a sort of write primitive to the secure VM and extract secrets later on. So we built this attack and demonstrated it a couple times previously. This one specifically through S3 boot script, but there is also can be done through SMI pointers and MMIO bars as well. Checking hardware configuration. So that's one really important check supposed to be properly implemented in all of the x86 systems to log the BIOS, to prevent the BIOS from directly having write access to the BIOS. And to doing this, there is the BIOS supposed to log one register, called BIOS control register. And this control register has some fields, and there is a spec which is defining what fields supposed to be set. And also CHIPSEC module which is checking this. And for example, here we see there is a Skylake system which is not protecting. And the interesting part that this module we added as a first module to the CHIPSEC. One of the main goals was to check the system to this one of the basic vulnerability which can be exist in the BIOS. And then again, I will repeat myself. Like a week ago, I buy a laptop, like really high-end laptop, 1.5K from some of the vendor. I run the test, and they're still not set BIOS control register. So there's still a bunch of system which didn't set there's one register in PCI config address space to log the BIOS and to make sure that the BIOS is at least doesn't have the easiest way to access, because if this is not set, then the BIOS is open fully and any malicious kernel driver can just easily override the BIOS, install implant, compromise on all of the system. Another good things about CHIPSEC that you not just can check the BIOS configuration and the different BIOS interfaces. Because you have the accesses to all of the other hardware interfaces, you can check other vulnerabilities. And for example, there was a vulnerability discovered by Christopher Domas in 2015, hardware vulnerabilities which allowing to make a privilege escalation from the kernel module to the SMM by overlapping APIC base with the SMM. Pretty good research. There was first research when someone exploited vulnerability by overlapping different MMIO ranges. Then later on, there was coming our MMIO bar overlap research and so on. Anyway, you can use the CHIPSEC module to check these vulnerabilities in your system and figure out if your system is vulnerable or not. All of the modern system is not vulnerable to this vulnerability. Next is memory configuration. There is, as I already mentioned, there is a bunch of registers which are supposed to be set. And there is a specific set of registers which are supposed to be set in the perspective of the memory controller. So some of the features which are supposed to be set and locked to making sure that the memory controller knows where is the register, where is the range which is supposed to be protected, what kind of features are supposed to be enabled, and so on and so forth. CHIPSEC has a module to check all of known registers which are supposed to be set. One of them is pretty important, is CHIPSEC, which I already mentioned this one. If this one is not set, then malicious attacker from the kernel with DMA capability can override SMM memory, and between SMM and the BIOS there is no boundaries, so if someone compromises SMM, they can automatically override entire BIOS. So there is the SMM is the runtime part of the BIOS, so meaning that system will be fully compromised. There was one case when in a 3-boot script you can disable this lock. So upon resume, you can say, I don't want to lock this register, and then when the system is waking up from the sleep, this register will be unlocked. We use it in one of the attack scenarios. So, as I already mentioned, if you didn't lock CHIPSEC, you need to have DMA capabilities. And usually people think about if you need DMA capability, you need external device and physical access and so on. That's true, but there are some devices which has DMA capability integrated device. And one of the device is the graphic. So you can use integrated graphic to send a DMA transaction. So there is something which is called graphic aperture, which is basically using the graphic page tables to access to any memory region. It was designed to making graphics working with the graphics stolen memory, but then it didn't check where you pointing this. So basically, if you point in somewhere in SMM, it will try to send a transaction, DMA transaction, to the SMM. If the CHIPSEC is not locked, the transaction will pass through. So basically, to build a full attack scenario, you need to unlock CHIPSEC somehow, or through a 3-boot script, or somehow differently, and then you use from the kernel driver, you use the capabilities from the graphic DMA to send the transaction and override the SMM. Anyway, the graphic DMA capabilities is accessible in CHIPSEC in the command line utility, so you can use it, you can play around. It's really useful, and especially it was really useful when the Windows 10 released this VSM technology, and before that when there was Hyper-V and they tried to enable different protection in the Hyper-V. These capabilities allow you to send a DMA transaction. In many cases, the configuration was not properly set, and you can use it to read the physical memory, which is not paged through the second level of translation, through the EPT translation. So pretty good capabilities allow you to make a lot of investigation. Or if you want to just to read the memory from some different sources, if you don't want, say, you're making the forensic investigation, and you use the OS capabilities to read physical memory, but you also want to use some other capabilities to read the same physical memory to make sure that no one spoof your interface. You can use this interface to read it and compare the difference and see if there is the same or not, if there's someone try to hook interfaces or not. So that was a section, pretty much it, about the vulnerabilities and how you can find them using CHIPSEC. I didn't cover a bunch of them. We released the materials from our recon training, which is covering all of the vulnerabilities which you can find using the CHIPSEC tool. But basically, if you run CHIPSEC main, it will run like about 20 different test cases, and there is a bunch of tools which is also available in CHIPSEC, which you can run manually to check specific vulnerabilities. So now, after we know a little bit about BIOS and vulnerabilities in the BIOS, let's talk a little bit about implants. As I already mentioned about this one, I will not stop too much. So one of the latest one, which has some information accessible in the public, using a 3-boot script vulnerability, implanting the macOS systems, surviving reinstallation, and even update BIOS. Don't have samples, so cannot analyze too much. Hacking team has samples, so everyone can just take a look and analyze it. Hacking team was pretty simple one. This one is making an assumption that the BIOS control register is not set. And in this case, you can just override the BIOS. And what they're doing, basically, they're injecting 3 modules. One of them is hooking the ready-to-boot event not hooking, it's actually setting the callback to this event. This event happening a little bit before exit boot services. So before exit boot services, before system is going to the OS boot flow and loading the OS, you have this event. And then if you set the callback, your code will run in. And that's what this implant is doing. It's basically running before OS. And what they're doing is they have the driver, NTFS driver. And the interesting part was that this NTFS driver was from the open source project, OVMF. So there is an open source project which is creating the UEFI-based firmware for the virtualization environment. And they just take the code from that project and use this code for their own malicious purposes. And the malicious purposes in this case, they just took NTFS driver, they parse the NTFS file system, and then they drop a file in file system. So that was all of the deal about this implant. So it has three components: infector, NTFS driver, and the file which they want to inject. How to detect this implant? One way to detect it, just to dump the firmware, compare the before and after infection, and see the difference. Another way is to detect this in runtime. So because they don't want to reinfect system and again, they put the flag, which will indicate that the system is infected. The flag is FTA. So if you just read the UEFI variables and find the FTA variable, that means the system is infected with this implant. There was some implants, PLC implants, released in GitHub, which is demonstrating that it's not really hard to implement the SMM backdoor implants or the BIOS implants. There's a couple links. One of them is here. You can go download and play in your system. To implant your system, you need to have need a physical access and SPI controller and find the SPI chip and reprogram the SPI controller, or find the vulnerabilities to make a privilege escalation to the SMM or to the BIOS. But pretty good PLC, really useful to play with. Okay, but what we can do if we don't know what exactly we want to detect, if you don't know if the system is implanted or not, what our strategy will be. So we need to somehow get the golden image, the information, the image which is basically we can trust. Because if you think about that, when you buy the laptop, you need to trust everyone who is delivering this laptop. When you travel in, you need to trust if you put in your laptop in a room in a hotel and so on. So basically, you cannot trust your laptop after some time. But can you trust your laptop when you purchase the laptop? If you trust the vendor and all of whoever is shipping the laptop, yes, you can. So you can dump the BIOS when you buy the laptop, and then you compare it later on. This is one approach. Another one, you can download the BIOS update from the vendor website, and then you can compare your BIOS with the BIOS from the vendor website. This is another approach. You can also use a different method to read. You can use the software method to read the firmware, or you can use hardware methods to read the firmware. Because if you use the software method to read the firmware, it's not 100% telling you that it is exactly what is in the firmware, because the interfaces which you use controlled by the firmware, so firmware can spoof this. This is pretty much it about concept. Let me see. Yeah, so that's how does it look like if you want to read the firmware with the hardware programmer. So you find the SPI chip, you clip it on SPI chip, and you read it. So not really convenient, but you got the real data. So something which is you can believe it's really in a chip, which is not spoofed. Then there is a two concept how we can use this image later. So there is a concept called whitelist. When again somehow you collected the known the good image and know the data of this image. So in case if you have many systems, you can compare different systems with each other. You just need to follow the same vendor and same model. Then you can compare them. You can also compare again with the BIOS updates and with the previous state of the same laptop. Interesting experiment which I did with this. I've collected all of the BIOSes from the vendor side for my Lenovo T430, and I run it against the BIOS which I have in my system. And that's what my small demo is. Let me show you this. One sec. Yeah. Yeah, that's 2 monitors. Give me a sec. Okay, almost there. So that's exactly what happened. Is I've collected all of the images from the BIOS website, BIOS vendor website. I've dumped the BIOS from my laptop, from the current state, and I run it against. And I figure out, and I run it my BIOS against that whitelist. I figure out one module not in whitelist. And I was sort of surprised. It's not like 100 of them. It's not look like false positive. It's just one. So then I spent it around 5 hours on investigating this binary, making the diff analysis, and figuring out what exactly wrong with this image. And finally, I figure out this is the false positive. So what this lesson is teaching me, that the vendor is not publishing all of the binaries which they're shipping in the systems. And there is, for example, this binary is from vendor, I hope. But the vendor never published this binary for the vendor website. So you're not really trusting this. Just because you make some analysis extra, you can say, yeah, that's probably false positive. That was a pretty cool experiment. So that is concept, we call it whitelist. Then there is CHIPSEC is supporting this, so you can generate your own whitelist. You can check then your system later on against this whitelist. So you can run a bunch of stuff using these modules. So second concept, we call it blacklist. Yeah, let me put in the presenter mode. Okay, so we call it the blacklist. So the idea is that if we know some things about what we want to detect, we can put this in sort of YARA rules, but a little bit more sort of UEFI specific, like what kind of GUID we want to detect, or what kind of functionality we're looking for, and then run it against the binaries and even detect the vulnerabilities. So that's the example of the detecting the hacking team UEFI rootkit. It's not really precise, it's just detecting GUID, but because this GUID is unique, you can really easily run and check and find this implant in your system. But the interesting part is that if you have good heuristics to define vulnerability, you can also run it and find vulnerability in the static analysis by doing this. And there was the thin pawn vulnerability has the good heuristics when you can run and find these vulnerabilities in your system in static analysis. So I was mentioning a couple of times already, you somehow working with the firmware, you comparing the hashes, but what this hashes is from. So the firmware in x86 system, UEFI-based firmware has the complicated structure. It's sort of small file system in the SPI chip, which has the volumes, it has a section, volumes, and then compressed binaries and so on. So here is the example of the hierarchy. We are looking for the last one. So after you decompress and unpack all of this, you got the sort of the last objects, which can be p-cov binaries, which is as regular p-cov binaries as we saw in Windows system, but they are Dixie drivers. So there's UEFI specific drivers, or there is also TE files. TE is the PI binaries. So when you extract all of this, after you decompress all of the hierarchy, you can compare this one. You can compare hashes of these files and against hashes from another file. So this is the materials for comparing. That's not giving you 100%, because there is a bunch of things which is not PE-COF executable. There is sections with data. There is some other sections which is also need to compare. But this is the easiest way to implant your system. So if you compare this one, sort of you will compare. You will try to find the easy implants. That's the output. How does it look like in CHIPSEC when you have all of the decoded flow? It's like a tree. So every time when you see the new block, that's defining the assumption which inside the previous section. It's like a file system. CHIPSEC is not a single tool. There is a bunch of other tools which is doing decoding, which is really useful. UEFI tool, UEFI firmware parser tool from Teddy Reed, really useful, really nice one. By the way, the decompression working is better now in CHIPSEC, so you can backport the fixes. Yeah. Flash ROM, really good and really useful to extract the ROM from the chip. So what kind of attributes we also can investigate? There is a bunch of things which we can take a look, and a bunch of things which an attacker may try to use to implant your system to make it more persistent. So it may change the layout of the spy chip, or somehow inject section or so. Binaries, which we already talked previously. NVRAM. So NVRAM is the configuration of the BIOS. The attacker may use NVRAM to store configuration or to use it for some other purposes. Runtime boot time variable also can be used by, actually this is the part of the NVRAM, by the attacker. Secure boot configuration is also the part of the NVRAM, is UEFI variables, can be used for the attacker, like say the system didn't change anything except the secure key certificate, the secure boot certificates in PK variable. That's something which you want to take a look deeply, because this one is allowing to bypass secure boot, and this can be a part of the attack scenario, and the attacker is compromising exactly just this thing. So really important to monitor it. Runtime, boot time, services. There is a UEFI system table which is represent the services which is BIOS having during the boot time and during the runtime. This is also can be a place when the implant can be using these tables. S3 boot script, as I mentioned, if the attacker has access to this, it also can use it to have sort of runtime implant, which will not implant, runtime root S3 boot script rootkit, which is basically will be really stealth and will run in every time when the system is waking, but there is no other evidence found except this. So if S3 boot script is accessible, it should be monitored. So meaning every time to time you need to check if there is any changes. Option ROMs in a peripheral device. CMOS, CMOS is legacy, but still may be used for some system. ACPI table, there was really good presentation from Google security researcher this year in RuxCon, how to use ACPI table to how malicious how attacker can use it to set implants in ACPI tables. SMBIOS not really can be used, but still it need to be monitored. Maybe there are some changes there. Hardware protection settings. So all of the hardware protection settings should be monitored because if there is implant, there was a way how the implanting came in the system. So maybe by monitoring the hardware protection setting, we will see the difference. Secure boot, I already mentioned this. TPM, if it is accessible. Different peripheral devices, file system, and the file partitions, including the boot partition with the OS bootloader. And yeah, that's artifact which we can use to monitor and find the implants. And somehow the attackers need to modify some of them to have a communication channel to the rest of the malicious code which is living in the kernel. So one of the interesting parts is UEFI variables, which I already mentioned a couple of times, which is basically BIOS configuration. There is the way how you can dump it and decode it in a CHIPSEC. So basically, you can decode it, and in human-readable format, you can see all of the names of the variables, GUID, attributes, and so on. Pretty useful. Many vendors have different variation of the format. CHIPSEC support like 5 of them. It's not all, but that's a lot of them supported, and you can read the UEFI variables from there. That's the example. System has may have hundreds of them. Some of them can be security related. Some of them can be may have even vulnerabilities because they're not supposed to be here, not supposed to be accessible, like setup variable. A lot of vulnerabilities run through that variable. Some of them can be indicator that there is infection, like FTA variable. You can use CHIPSEC to decode the secure boot configuration, including and extract certificates, dump the runtime and boot time variables, boot time service tables, dump CMOS, everything which we have there in previous slides. So dump ACPI tables and compare the difference. It's also supported in CHIPSEC. So as you mentioned that for implants, we have a bunch of things to monitor and a bunch of things which implants can use to build them functionality, communication functionality with other malicious component in the system. So now there will be a really short section about how we can use CHIPSEC to analyze virtualization environment. So as I already mentioned a lot about CHIPSEC, you can use to read different hardware configuration. Because hypervisor need to emulate all of this hardware configuration for the guest, so then you can use CHIPSEC to read what exactly hypervisor is emulating and where is maybe some vulnerabilities there in some interface not properly emulated. You can investigate exactly what was emulated and how. So, and as easy as you can build the IO visor, you can build PCIe visor, MSR visor. You can fuzz all of the hardware interfaces to making sure that the hypervisor is properly emulating this. Also, you can build the hypervisor-specific visors to fuzz the hypercalls, and you can use the CHIPSEC to dump the hypervisor configuration. So in case if you're running the CHIPSEC in a host OS for hosted hypervisor, say VirtualBox or KVM QEMU, you can dump the MMIO configuration and VMX configuration for the hypervisor using the CHIPSEC tool. Pretty useful for investigation, forensic, like say someone compromised the hypervisor or your backdoor is modifying the hypervisor. You can dump configuration before and after and see if there are any changes. So by using CHIPSEC, we find a bunch of vulnerabilities. One of them was in Zen, in one of the hypercalls, use after free. It was pretty interesting. You can take a look offline. There is a PLC to reproduce the bug. Also, we built the MSR visor, really simple visor, but back in 2015, even this visor gave us some of the vulnerabilities in VirtualBox. Also, you can use this to fuzz the I/O interfaces. We didn't find this vulnerability before, but we reproduced this after that was discovered. So known vulnerabilities can be reproduced by this visor as well. So pretty simple visor. And then a couple examples, how does the hypervisor configuration look like? So basically, when you use the CHIPSEC to dump the hypervisor configuration, there is a state of the VM, state of the paging for the VM, and state of the VMCS. All of this is accessible through the CHIPSEC if you run it in a hosted OS with the hypervisor. And also we demonstrated that we can use CHIPSEC for the attack purposes. So if there is any hardware interfaces that is accessible, and in this case, in Zen DOM0, the S3 boot script was accessible, and we use it to get the access to the hypervisor. Yeah, that was another example of the VMCS. And there is example of the dump the VTD tables from the hypervisor. With this, I'm almost finished. So first of all, There is a bunch of interesting tools right now, including CHIPSEC, which we can use to make an investigation and the platform and the hardware and the hypervisor virtualization environment itself. We need to think more about how we can detect implants, because in many cases there is a really hard task and has a bunch of false positives, especially if we're talking about peripheral devices. Yeah, that's basically it. Any questions?
So you mentioned you relied on the vendor website for the notebook
Yeah.
to check if you had if they were publishing all of the firmware. Do you know if there's any efforts to get firmware vendors to provide copies to like the National Software Reference Library or anything like that to make it easier to?
Oh, that will be awesome. So the question is, can we, if I understand correctly the question, is there any way then we can ask vendor to publish more precisely hashes of the binaries to make it like sort of library? Is this what the question?
Yeah, it's the National Software Reference Library. It's
Yeah.
Digital forensics reference library for software.
Yeah, it will be awesome. I never heard that they will doing this. I mean, they're not publishing too much. So there is two interesting things you can find if you search a lot in a vendor website. You will find a bunch of stuff which is not supposed to exist, and you will not find what you're looking for. So. Any other questions? Yes.
So there's obviously a lot of moving pieces in terms of firmware in security. And I just wondered, like, you've obviously had your in the space a lot. Like, do you feel like the security of firmware? I know it's like a broad question. Is like improving?
Oh yeah, this is improving. So when we started, there was a lot of so there was like when we started, we bought a lot of laptops. Many of them was failing. And then like a year or 2 years ago, we buy the second generation, same laptops. That was much better, and then there was much better. But the thing is, if you're not checking it and not periodically sending the reports to the vendor, there somehow the bug is coming back. Or they discover a new one, the same one which they fixed it previously. So there's a process when you need to sort of run it again and again and making sure that everything is sort of correct. But they're improving a lot. So to compromise system right now is much more harder than 3 years ago. If there is no easy bug, that will be much more harder. Sometimes easy bugs still can show up, but there is much more harder. The thing is that if you find some software bug like a SMI pointer, in multiple cases it may be exploitable because there is no ISLR and depth there. But to log the configuration is pretty straightforward task. So there is less bug about platform configuration, but there's still bug about implementation.
So do you feel that's true across platforms as well?
Did you have what?
Across like do you feel that's true?
It's not working yet. I don't
Do you feel
know.
that's true across platforms and architectures as well?
Across platforms. I mean, we run some, you mean cross platforms like ARM, x86. So we start looking in ARM this year. That's completely a different topic to discuss. There is just different concept about security there because say MMIO BAR attack is not working in ARM at all because it has the SoC and all of the device has constant addresses. So they're not overlappable. So, but some of the things is really interesting because in ARM there is not a lot of documentation about SoC of the ARM. So, but if you think about that, there is a bunch of devices. Some of them has big MMIO ranges, but you don't know what this device is doing, and there might be an issue there. So there may be an issue when there is some of this MMIO registers will be an address to the buffer, and then you can overlap this. But the point is, there is really hard to figure out it because for ARM, if you will want to figure out, like say, for the ARM Nexus 6P, you want to figure out, you rooted your phone, and you want to figure out like what the register is there. There is no public documentation. You can do that. If you go and buy a reference board, exactly same SoC as this phone, as with reference board, they will provide you a spec. Then you can map this spec to your phone and sort of make an investigation, but it will take a while to make this all connection. So there's different concept about that. There still can be a problem, but different problems. And yeah, unfortunately, we didn't spend that much time to really good understand all of the ARM security. So we have some basic stuff, but not advanced one. Go ahead.
So it sounds like a lot of these vulnerabilities have been fixed with patches to the platform code. And even if they're in the SMI handlers, like we look to our ODMs to look to the device manufacturer who provides that SMI handler to them, it's just a software patch.
Many of them, yes.
When's the last time you couldn't patch these vulnerabilities in software?
I mean, I'm not a BIOS vendor, so I can just guess. There can be cases when it will be harder, for sure. And yeah, but that's a better question for BIOS vendors. But many bugs are software bugs. So the easy answer is a lot of bugs can be fixed in a software with the properly software validation. Some of them may be tricky because they are like a raw hammer, for example. That bug is not really easy to fix in software. You need to make a lot of efforts all over the ecosystem. So, but yeah, many bugs can be fixed in software. Yes?
So from what you say, it doesn't look like the vendors are taking this seriously, or there is a coordinated effort to fix this.
Taken seriously? I try to,
Yeah, sorry,
yeah.
taken seriously. I mean, it doesn't look like there is a
No,
coordinated effort to
so they taken it seriously after you report the bug.
Yeah, that's what I mean is you need to report it. There is no proactive.
Many of them is doing the security validation, and especially last 3-5 years. I just don't know exactly how does they work, but I believe they're doing a lot of work because some of the vendors is now much more better than previously, but some of the vendors still waiting until someone third party will find things. And especially some of the vendors, they have a sort of 2 lines of BIOSes. One line for enterprise, which is really good. And another one is for everyone else, which is, and that one, they're not taking too much attention, so you need to report in that space. So that was one of the issues. The point is, it's not just about fixing the bug, it's also about delivering the update. So delivering an update for BIOS is not easy task because you're always in the middle between breaking system and not. And you need to count all of the combination of the software which can be used, different combination of the BIOS. And that sort of validation process for fixing, it's much more longer, and delivery also not standard and longer. So that's why even if there is a BIOS fix, so say this system is vulnerable for a couple bugs, maybe BIOS fix already there. I didn't check, but after I reported, there is like long time when the release happened and then the update happens. So that is, but some of them is making much more better work, much more. So the thing is, for known vulnerabilities, they're doing a lot, but they don't doing too much research to figure out a new one. So if you find some new one, it may be affected all over.